A spacecraft is leaving the surface of TRAPPIST-1F, which has a mass of 0.68 times the mass of the Earth and a radius of 1.045 times the radius of the Earth. If the mass of the spacecraft is 3,800 kilograms, what must the initial speed of the spacecraft be to escape the planet's gravity? Would this be greater or less than the speed needed to leave Earth? How would the escape velocity change if the radius of the planet was halved? If the radius was halved and the mass of the planet doubled? The escape velocity is defined as the initial velocity necessary so that when the spacecraft is very far from the planet, its velocity is zero. Our knowns are the mass of the planet, which is 4.06 times 10 to the 24th kilograms, the mass of the spacecraft, which is 3,800 kilograms, and the radius of the planet, which is 6.66 times 10 to the 6th meters. Our unknowns are the initial velocity of the spacecraft. To find v-escape, we will define our system as the planet TRAPPIST-1F and the spacecraft. The energy principle tells us that the change in energy of our system is equal to work plus heat. Assuming no work is done nor heat exchanged with the surroundings, the change in energy of our system is zero. This means that the final energy of the system is equal to the initial energy of the system, or that the final kinetic energy plus the final potential energy is equal to the initial kinetic energy plus the initial potential energy. Conservation of momentum tells us that if the planet spacecraft system is initially at rest, then the momentum of the planet must be equal in magnitude and opposite direction to the momentum of the spacecraft. Since the planet is many orders of magnitude more massive than the spacecraft, this means that the velocity of the planet will be almost zero. Thus, we can neglect the kinetic energy of the planet in our energy accounting. Only writing the kinetic energy terms referring to the spacecraft, our energy principle statement then becomes 1/2 mv final squared plus negative gmm over r final equals 1/2 mv initial squared plus negative gmm over r initial. Our final situation is when the spacecraft is very far from the planet. In this limit, r final goes to infinity and v final goes to zero. This means that the final potential energy has infinity in the denominator and thus approaches zero, and that the final kinetic energy also approaches zero. This gives us 0 equals 1/2 mv initial squared minus gmm over r initial. Bringing the initial potential energy term over to the other side and multiplying both sides by 2 over m gives us v initial squared is equal to 2 over m times gmm over r initial. The mass of the spacecraft cancels, leaving us with 2 gm over r initial. Taking the square root of both sides, we find that v initial equals the square root of 2 gm over r initial. Since the spacecraft begins on the planet's surface, we now have an expression for the escape velocity, which tells us that the escape velocity is only dependent on the planet's parameters, specifically that v-escape equals the square root of 2g times the mass of the planet over the radius of the planet. Plugging in our values, we find that the escape velocity of TRAPPIST-1F is 9.0 times 10 to the third meters per second. Now we will perform a unit check on our symbolic result. Inside the square root, g has units of meters cubed over kilograms second squared, m has units of kilograms, and r has units of meters. The kilograms cancel and one of the meters cancel, leaving us with meters squared per second squared inside the square root, which gives us meters per second as we desire for a velocity. Now we will compare the escape velocity of TRAPPIST-1F to the escape velocity of Earth. We know that the mass of Earth is greater than the mass of TRAPPIST-1F, and that the radius of Earth is less than the radius of TRAPPIST-1F. Since our expression for escape velocity is square root of 2gm over r, The escape velocity of Earth will have a bigger quantity in the numerator and a smaller quantity in the denominator. Thus, the escape velocity of Earth should be greater than the escape velocity of TRAPPIST-1F. If we Google the escape velocity of Earth, we find that it is approximately 11,000 meters per second. This both agrees with our prediction and confirms that our numerical value is of the correct order of magnitude. Now we will find how the escape velocity would change if the radius of TRAPPIST-1F were 1/2 its actual value. To do so, we will use ratios. The ratio of the new escape velocity to the original escape velocity is given by square root of 2gm over r prime all over square root of 2gm over r. Bringing everything under the square root and then multiplying by the reciprocal of the denominator, we find that everything except the radii cancels, and we have square root of r over r prime. This becomes square root of r over 1/2 r, or square root of 2, which is approximately equal to 1.41. Thus we find that if the radius of TRAPPIST-1F were halved, the escape velocity would increase by a factor of 1.41. Now we will find how the escape velocity would change if the radius were halved and the mass doubled. The ratio of v escape double prime to the original escape velocity is given by square root of 2gm double prime over r double prime all over the square root of 2gm over r. Once again, bringing everything inside the same radical and multiplying by the reciprocal of the denominator, we find that everything except the mass and the radii cancel. We then have square root of 2m over 1/2 r times r over m, or square root of 2 over 1/2, which is square root of 4, which is 2. This means that if the radius of the planet were halved and the mass of the planet were doubled, the escape velocity would double. Since our ratios are dimensionless, and we have already checked our units and order of magnitude, we are done.